Okay, what did we talk about last time? Chemical potentials, yep. What's the point of trying to talk about chemical potentials? Related to what? Yeah, it's related to equilibrium. Again, we're trying to get to the point where we can discuss what equilibrium really is. Another way to reframe chemical potentials in equilibrium is through something called extensive reaction. And you guys know a lot about this intuitively without ever actually seeing it before, most likely. We're going to talk about extent, and it's got the symbol capital epsilon, which I am horrible at drawing. So if you ever just see something that looks like a squiggle and you don't know what it is, that's what it is. I really have to slow down. That's still not good. I don't like it. And what extent of a reaction can tell you is the reaction progress. Is it at equilibrium? Is it not at equilibrium? Do we need to consume more products or more reactants? You guys intuitively know that based upon the value of K. If K is if K is greater than 1, what do you know? Yep. We'll see if any of that came through. So extent of reaction, we measure the progress of a reaction. We can look at some parameters here. So am I even recording? Yeah, it should be. All right. Sorry, Will. Anybody know what these symbols mean? Not working. I'm giving up on this one. I think they're both dead. That charging port doesn't work worth a shit. I might just make another video for him. All right. I'm going to have to shut the door. Is everybody okay with that? If you don't mind Dr. B yelling at us or somebody. Okay. This is the moles of some species I at time t. What's this other thingy?
The moles at time 0.
Yep. Anybody have an idea what this nu is? It usually is frequency when you're talking about quantum stuff.
Wait, what's it called again? The letter. What's it called?
Nu?
Yeah.
Yeah. What this is it's actually the stoichiometric coefficient for whatever reaction we're considering. It's negative for reactants, and it's positive for products. We're going to investigate this. We're going to look at some chemical reactions to try and find out what this means. Before we do, though, we're going to express extent in another way. So if you're considering a chemical reaction, if you look at the change in Gibbs energy with respect to the extent, holding pressure and temperature constant, you can figure out delta G of a reaction. Mathematically, what's a derivative? Or what can you find from a derivative?
Changes.
Changes, yep. So, yeah, slope is what I was going for. Really, we're talking about a slope here. Okay, so if we imagine the potential energy surface, or like every possible configuration that we could have this chemical reaction happening, and keeping track of delta G, we can learn some information about if we're at equilibrium, not at equilibrium, and which way do we have to shift to get to equilibrium. So what we're going to plot, we're going to have G on our y-axis. We're going to have extents on our x-axis. And what color do we want to pick for our line?
Green.
Green? Damn it. Not the color I have. Is that why you picked it?
I don't know.
Well,
It's the
at
only
least,
one, it's the only one not on the board.
oh, that one doesn't sound so bad. Well, I don't know about you guys, but like, there are two noises.
The chalk noise.
Chalk noise, oh yeah, these ones are so much better. The other thing is mechanical pencils, hate their noises, can't stand them at all, drives me nuts. And people's lips smacking when they eat, I just go into a rage. What's that? Oh yeah, I can't hear it, so you're good. I like the hum of my servers in the background. Okay, so let's look at it at some certain points. Let's say we want to consider the slope along there. Can people see the red or the pink? Slope along here. And the slope along here. Keep it in mind, remember, we're looking at the slope, right? What's delta G here? Yep. What about for the blue region and the pink region?
Negative for the pink region.
For which one?
For pink one.
Yep. And blue one?
Positive.
Okay. So if you look at these guys, you can figure out where and when you're at equilibrium from this, which is kind of cool. Okay, let's look at a chemical reaction though, one where we can calculate the extent, so we're gonna see some interesting stuff with that. Example, following reaction is set up with the initial conditions. we're gonna look at a couple different scenarios. First one we're gonna look at is determine the extent each species if all the P4 reacts. Okay, erase this side too. Okay, we gotta calculate the extent for each species. Yeah, let's do it over here. So we gotta get H2 P4. Anybody know what pH3 is called? It's called phosphine gas. It's a dangerous gas to work with. You don't want to work with phosphine gas. A lot of times it will polymerize and it'll smell like fish. If you smell fish and you're not working with amines, get away. Okay, we gotta calculate these things. We wrote previously that it's, Ni minus Ni. Right? Okay. Here's where we're gonna have to do a little bit of math to remember some limiting reagent stuff. Which one of these do you want to look at first? Which is the easiest to consider? Yeah, P4 is the one I would look at. We don't have to really do any stoichiometry or math. Okay, how many moles are we going to have at the end of the reaction if we consume all of it?
0.
Yeah, minus. What did we start with?
2 moles.
Yeah. And what are we going to divide by? Yep. There are no units on that though, right? So when you divide through, what are our units going to be and what's the value going to be?
2 moles.
Yeah. Which one do you want to do next?
H2.
H2? Okay. How much H2 do we start with?
18.
What should we put for that, the new for H2?
-6.
Yep, because it's a reactant. All right, we're consuming all of this, and there's a 1:6 ratio, right? How much H2 is gonna be left over?
6 moles.
Yep. Okay, math that out. What are you gonna get?
2.
Yeah, 2 again. Actually, I guess I shouldn't put labels, but we'll keep it that way. Extent of this guy. What's the initial amount of phosphine we have?
1 mole.
Yep. Stoichiometric coefficient?
+4.
Yep. And if we consume all 2 moles of this, how many moles in the end are we gonna have? How many do we make?
4. Is it 8?
Yep, we make 8. We had 1. What's the total at the end?
9.
Do the math. What do you got?
2.
Yeah. does that tell you about our concentrations? Is this, and thinking about delta G? Again, we have to look at the change in G too. But if you look at these extents, you can see that they all match one another, right? Do you want to do another example of this or no? How many people say yes? Raise your hands. People say no.
Is
Raise your
it, is it an example where they still all match each other?
Yeah, they're always going to match each other.
What
If
is
they don't, you've done something wrong.
What does it mean?
What does it mean? We're gonna talk about that.
Okay.
Okay. We could look at, let's say we change it up a little bit. We say all of this reacts to form reactants. What do you think the sign is going to be for extents? Yeah, it's going to be negative. Okay. So there's a happy ground to reach equilibrium. What you're meant to get out of this is the magnitude of the extent is the same each product and reactant. Two, if E is positive, if E is positive, the reaction will go towards the products. And when it's negative, where does it go? Yeah. Okay, but what did we say we had to keep track of if we want to know? If we want to know about equilibrium, if we want to know how a reaction will proceed, or we're changing moles, what do we really need?
Delta G.
A delta G, and how are we going to find delta G? If you think back to that little differential, what are things that we had to keep track of?
Change in G.
Change in G, yeah, we want change in G.
Change in extent.
Yep, change in extent, that will tell us, keeping what constant?
Delta zero.
Yeah. So extent, there's also another way we could look at it. If we look back to like how we express this for the daily problem. Yeah, we need enthalpy, we can look at it through enthalpy. One other big thing that we haven't,
Chemical potential.
we need chemical potential. I don't see chemical potential in here. Can we relate extent to chemical potential? If we can do that, then we know everything, or at least have ways to figure out everything about the system. So does extent change, or excuse me, what changes when a chemical reaction happens? What changes in a chemical reaction for our system? If we let this happen, what's going to change?
The moles.
Yeah, the moles. And specifically, if we're talking about an individual one. back at extent again. How do we calculate extent of some species I?
The change in molar species
Uh-huh.
over stoichiometric coefficient.
And Lily, you said it, the change. What's another way we could represent this thing?
Delta I.
So let's say we have this. Right? That's similar. Let's manipulate this around. Let's get dni by itself. What's that going to be equal to?
Multiply.
Yeah, just multiply it through. Get that. Okay. What we're going to do next, we're going to sub this into the natural variable equation for dg. So returning natural spin. We get dg is equal to what?
BDP minus SDT.
Yep. BVP minus SDT. What else do we need because we're changing compositions?
Plus the summation
Yeah.
UI dni.
Okay. At constant pressure and temperature, how does dg change? Just to make things a little simpler for us.
UI times D and Y.
Mm-hmm. Let's sub an extent in this, in place of this guy. So we get dg is equal to what? Same summation, what else we got?
UI.
Yep,
That like V thing.
yep,
Then D epsilon.
still don't look like it's favored anything right now, right? What do we know about this term here? Or what did we just show for this term here? Let's say I'm looking at I or J or K or any other things. What do we know about this?
It's the same.
Yeah, it's the same for all of them, right? So even though we have this ugly summation, what could we do with this?
Pull it out.
Yeah, pull it out front, because really, that's true, right? So let's pull it out front. Since this thing is the same for all species. It should be a little bit better. It shouldn't be degrees, partial. And what's gonna be held constant here?
P and T.
Yep. And what's that equal to?
Delta G reaction.
Yep, it is. And what else?
The summation UI.
Yeah. Times stoichiometric coefficient. So now really we just have to know the chemical potential and the stoichiometric coefficient, and we can figure this thing out. I said, or I promised we would tie this into equilibrium. We know at equilibrium, what's delta G equal to?
Zero.
Therefore, what's EG equal to?
Zero.
Okay. Then at equilibrium. What's that thing equal to?
Zero.
What else is equal to zero?
That summation.
Yeah, that summation thing. Okay. Probably not this class, but next class, we're going to use this and show how it relates to two things. We will use this to discover K, and then good old Q. You remember what Q was?
Or different Q.
Different Q. Back to Gen Chem Q or analytical Q. Do you remember what it tells you?
So when it's
I
equilibrium.
don't even remember
Yeah,
Q.
if you're at equilibrium or not.
Right here, I kind of have to remember
It's
it.
known as reaction quotient.
Oh, yeah.
Yeah! See, you guys knew it.
I'm convinced I didn't learn that.
Probably did
I'm
it.
convinced I had no clue what that is.
You probably did it for like one Gen Chem homework question or test question and then just blip out of your brain for it. I don't know in analytical if you had to stare at them a million times or not. Yeah, you did. Okay. Shannon's like, yeah, those were bad times.
No, we had to do this one where it was like, here's greater than K.
Yeah, I remember that.
Yeah.
Oh wait, I do remember that.
Yeah, I kind of
That's
have to
stupid, I
remember
can't
that.
do it.
I
But
remember-
Lily, I'm glad I have you so deeply programmed now when you see a Q, you're like, heat. No questions asked.
No, but then in
But that's a little
physics,
Q.
we don't use Q. It's
What do you
some,
guys use in
or no, maybe
physics?
that's something else. Oh no, it's potential energy and internal energy.
Oh, yeah.
Potential energy is U, and not internal energy, and it, oh my gosh, it
Yeah, I
messes me up so
I
bad.
dislike that one a lot, and there's many reasons, and I'm sure Dr. Pianka doesn't like that one. And Dr. what's Anisha's last name?
Barjwa or something
Barjwa.
like that.
Yeah. He just makes me call him Anish all the time.
He tells the students to call him Anish.
Yeah.
That's probably easier. It's,
If not, it would be Dr. B, but there's already a Dr. B.
yeah.
And she is the only Dr.
Yeah, she-
No one
yeah.
else can
She
be
is
Dr.
Oh,
B.
yeah. Okay, so we're gonna get here. The next bit of stuff we talk about is gonna seem unrelated. It is related to this, okay? You're gonna see, we're gonna go through this bit, and then we're going to connect it back to here. So if you feel like you are lost in the forest, just push through this next bit, and we're gonna get back to that, okay?